you may be um, yeah. Hello.
Sir, yes, sir. You're audible, sir. You are
Okay,
audible
no.
to us.
Like, okay. Just I want to confirm it. That's what.
Yes, sir. Yes.
Yeah. I can see some pop up here. I don't know whether you're distracted by this pop up.
No issue,
Some
sir. No
pop.
issue from your side, sir. No issue.
No issue from my side. Okay,
Yes, sir.
but okay, no issue then. In that case, then I am getting some pop-up message onto my screen. So regarding the recording of this, that's what I'm asking. Okay, otherwise there is no issue. Yeah, let me continue. And then finally, the design rules of additive manufacturing. So finally, I'm going to discuss some of the design rules of additive manufacturing. So this is what I have planned for the next 1.5 hour, and followed by the discussion. That is what I have planned. Yeah, let me go to the next slide. Yeah. Yeah, so if you see the AM process chain, typically we need to start with a CAD model, which it has been, say, generated from your CAD/CAM CAE package, or even it could be done through a reverse engineering system also. If you have already the physical model or the product as already existing, probably even you can start with reverse engineering it and getting digitized it. So that is also one way of doing it. Or even you can take a DICOM image in case of a medical, say, application, where even your DICOM images further it has been sent converted as STL file. So it could be right from the scratch through a 3D modeling going to be the start point, or even it could be a point cloud data which you will get in the reverse engineering, or even it could be a DICOM images further it has been converted in STL file. So that is going to be the start point of the typical AM process. Will start with that, and then which we need to convert the data, as we know that the de facto standard, so as an STL file, though this technology started 32 years back, the still STL file is going under the de facto standard, even though you had recent times AMF, 3MF, OBJ.mlt files are there, but still STL file is going to be the de facto standard in this AM industry, and which we need to further convert as an STL file and transmitting it through a network, or where you have a facility of additive manufacturing machine, so which it has been connected with interfacing software. So in that interfacing software, we are going to check, and why you want to check it means, unfortunately, you don't have any mechanism in the CAD software, neither nor with the interfacing software, you don't have anything to measure, or to diagnose whether there are some errors in the STL file or a CAD model as such. So for that reason, which you may be checking it, and after checking it and after finalizing, it's everything is fine, means it's a watertight model, and then you will be preparing something like a code or a command, so that is going to send to the machine. So typically, you are going to preparing a build setup or the cross-sectional images, so that is going to send to the machine. So once you have done that, you send that codes to the machine. You may have different technologies. I don't want to go into that various technologies. Maybe other speakers may be talking about those technologies. And then once you have completed your fabrication layer by layer, first layer to the last layer, and the last step is going to be the post-processing. So again, the post-processing depends. the type of technology you have used. Sometimes you may use a curing oven, UV curing oven like a SLA or a VAT-based system, or sometimes you may use ultrasonic cleaning for cleaning of the models, and we need to remove the support. Sometimes we need to through manually we need to remove, or by using some solvent, or even you may use some chemical materials, or sometimes you may use furnace treatment also. That purely depends on the type of AM technology you're using it, and of course the application of that product. So it demands 100% density, say for example, and then you may go with some sort of hipping process, or if you're not satisfied with the as built, the the quality of the parts as built, you're not satisfied, even you may go further post processing it. So these are the typical steps involved in any AM process chain. So let us focus on the design aspects. So this is the all about the various steps involved. So let us focus on to the design aspects. So then for that, first let us see the process plan involved in any typical additive manufacturing process. So that the process plan, say, consists of which we need to start with the CAD model. Just now we have discussed, say, probably you start with the true geometry. What do you mean by a true geometry? Is a native file format. If it is a Pro Engineer, it may be .prt, and it may be a CATIA, it may be .part, or it may be DWG in case of AutoCAD. Or basically, the true geometry is a geometry where you have used some CAD/CAM CAE package to model by using some geometric modeling technique or parametric modeling technique to say make the model. And as such, you cannot send this true geometry to the AM machine, which otherwise in turn we need to convert it as an STL file. So STL file, basically it is a the triangular mesh, and you can control the triangular mesh resolution by varying the parameters like chord height, angle control, step size, and so on and so forth. So once you manipulate with the parameters, then you can come out with the best resolution of this STL file. Why you want to check with the best resolution? So as we know that this is a technology garbage in and garbage out. So if you're not, say, giving a healthy file or a accurate file or more precise file to the machine, you are going to get only the garbage out, like whatever you send, you are going to get from the machine. So you have to be careful, like while working with this sort of say resolution in CAD domain itself. So where in turn the accuracy will depends on your discretization or the resolution of your models, right? Say, sorry. So that is the first step. You do it in a CAD to the STL file, where we need to do that. And then next step, your STL file is getting sliced. While slicing your STL file, so we can have
Sir, your voice is not coming, sir. Ravi Kumar, sir.
Sir, message him. Message, sir.
I'm calling to him.
Yeah.
hello, Chari.
Hello, sir. Your voice was stopped in between, so he was trying to call you, sir. Now it is audible. You
Yeah, actually there is a hitch from my side. I think
yeah.
the power went off. I
Yes,
think now
sir.
it's okay.
Yeah, now
Yeah, now it's
not-
okay. Now it's okay.
Okay.
seeing the sort of resolution in the STL file, say, then how it is getting sliced. So next step could be on the slicing of your STL file. So these slices, so we need to say select a certain resolution, means the layer thickness, and that will dictate your say if you are going very thin layers, we can get very accurate parts, but that is at the cost of build time. So the build time is high, and where you have a contradiction or a trade-off between your accuracy and the build time. So our job is to say choose a right layer thickness to optimize your accuracy. So then your good design for additive manufacturing is also, it talks about all these steps which we need to optimize, these each and every step which we need to talk about in the process plan of additive manufacturing. So for slicing, and even as well as once you slice it, you are going to generate the contours. So first you are going to generate the contours, and those contours are the empty contours, and which we need to fill it up. So where typically you may use a G code to filling up these contours. So again, you have a lot of freedom here. How do you get fill it up? So then you can have a different filling density, or you can have a different path strategy. So you can say choose your
Sir, sorry for
the
interrupting you, sir.
requirement. Yeah,
Welcome,
please.
sir. Sorry for interrupting
Yeah.
you. Sir, the screen
Yeah,
is
yeah.
not good, sir. Actually, the screen is something shaking. The font is not proper, sir. Can you rejoin, or can you reshare the screen?
Yeah, I will do that one. Maybe problem with, I will reshare it.
Yes, sir.
I will stop sharing, and again I will share it. Okay. Yeah, let me do that. Is it now okay? Is it screen is coming?
Yes, sir. Screen is coming, but
still that problem.
Still the problem. Yes.
I'm not sure whether.
Sir, can you log out totally?
Yeah, that may be better option.
Yes.
And I will log out and I will rejoin.
Yes, sir. No problem, sir.
That may
we
be
will change. We will wait for you, sir.
Yeah, I'm leaving it right now.
Yes, sir. Okay, sir.
And hello, Chari?
Yes, sir. You are joined, sir. You are joined in the
Okay,
meeting.
let me share
Yeah.
the screen.
Please share your screen, sir.
Host disabled.
I will give you, sir, 1 minute.
I think it should be given some permissions.
Yes, sir. Yes, sir. Now you can share your screen, sir. Please check.
Yeah, 1 minute. I think now I'm getting. Yeah, I'm able to share now.
Yes, sir.
Now the screen is visible.
Yeah, screen is visible, sir.
Let me go to the.
Yeah, font also good now.
Okay. Now is it okay?
Yeah, now it's good, sir. Now it's good.
No, actually there was a power failure.
Yeah.
It's heavy rain here. Heavy rain. Yeah. Yeah, and now it's okay, right?
Yeah, it's okay, sir. It's okay, sir. Thank you.
Yeah. Okay, Chari. Thank you.
Okay, thank you.
So where we were discussing about the slices, how do you get say from slice to the G code or probably the toolpath generation? So you can say first get uh, get the outer contour and it will be filled with you have a lot of freedom here to how do you get fill this contour. Maybe you can go in several fashions, like which it ultimately dictates your the requirement of the in terms of say quality, in terms of mechanical properties, in terms of say physical properties. Your toolpath will play a lot of the vital role in terms of getting this. So we'll discuss that also, like various toolpath strategies and how we can improve the part quality. So as such, which we need to focus on all these aspects. And apart from these aspects, so we need to say talk about the part orientation. So part orientation or the build orientation. Say so for example, if you take the CAD model, so we can build as vertical let's say direction or some 45-degree inclination, where you say at the moment you are fixing this orientation as vertical orientation and you are slicing it and you are building from the first layer to the last layer, and which we can see the error for this. So you try to calculate the cumulative error at the each and every layer, and you try to quantify what could be the total error or the deviation. It may have some say X amount of that, and if you have other sample which it has been made 45-degree orientation, and if you are using the same layer thickness and trying to quantify the error, so definitely you have a different quantity of error than here. So what I'm trying to say, your orientation is going to play a vital role in terms of accuracy. Not only accuracy, so the build orientation will affect your build time, accuracy, mechanical properties, physical properties, and so on and so forth. So your orientation, the fabrication orientation, is going to play a vital role. So in terms of stepping, that is while slicing, say we may anticipate this sort of error. The you cannot eliminate 100% this. Why? Because by nature it is getting stacked, these layers. So that error may be tedious wherever you have the free-form surface, especially if you are having a flat surface, your staircase effect may not be the more quantifiable. But whereas if you have wherever you have this sort of free-form surface where you need to anticipate say staircase effect, then how do you tackle that staircase effect? As such, you cannot eliminate, but you can minimize, maybe by manipulating say layer thickness, one way of doing it, or by adapting a different slicing algorithm or slicing method. So then we'll discuss that also in the further in the upcoming slides. So which we need to say properly select a part orientation. Then you may get doubt that what could be the optimum orientation, right? So you may have several criterions in your consideration. Then what is your consideration for fixing your part orientation. That also we'll discuss. We have several criterions that should be say which we while fixing your orientation. And of course the layer thickness, as we discussed, if you are going with very thicker layers, so you have more error. And if you are reducing the layer thickness, you may get better accuracy, but that is at the cost of say build time. So where if you are reducing the slice thickness, you may get better accuracy, the resolution, but that may unnecessarily increase the build time. So where we need to come out with an optimum solution for this. And next one is a support structure. The support structure, again, if you vary the orientation, so it may consume a different amount of support structure. So means the quantity of the support structure that it's going to say consume, it will vary from one orientation to other orientation. So, and even if you talk about so to minimize the support structure, and then you can come out with a design for additive manufacturing strategy to say minimizing these supports. But not all the time your supports are could say bad or the curse, but sometimes it may be the boon for you also. Under what circumstances, then we'll discuss that. So the support structure is a major concern for a design for additive manufacturing of your components. Then first of all, we'll focus on the part orientation parameter. So this part orientation can have say usually five criterions. So what are those five criterions? Like say the part height criteria is a one where if you follow this criteria, so you may be fixing a orientation which is of minimum Z height. So that is why minimum Z height? The minimum Z height will consume the minimum number of layers that you are going to fabricate. Means the build time is less, means the build cost is less, right? So that may be the one of the criterions that you follow for fixing the part orientation. Or other second criteria may be your focus will be on the surface finish or the surface quality. So then that may become the other criteria. So you will be focusing on the part quality or the surface quality of the product that you're going to fix that orientation. But that orientation need not be the same as we discussed previously, right? And even you have another third criterion that maybe the area of the base. Means if you are having a better foundation, then your things will be smooth. Means on the substrate or on the platform, if you're giving a better say base with a more support, and then it will be having say less viability for damage or say failure of the component while building. So which we need to have, the area of the base should be more on the part that is resting on that. Or even some orientation may give a better mechanical property. You cannot anticipate the same mechanical property in all these orientations, the possible orientations which we are talking about. So some other time you may be looking for better mechanical property. Then how do you get fixed your part orientation? Or maybe you may be much worrying about the support structure. Why? Because it is also equally costing you. Like you have a model material, say X rupees, and even it may be the support material also X rupees or X minus delta X rupees, but almost it may be the on par with the cost of the support material. Then how do you minimize the usage of the quantity of the supports? That may give you the another solution or another criterion for fixing your part orientation. So say we can summarize these five criterions in this way. So if you take a typical say design, so where you have designed in a CAD software and this is what you are going to fabricate, and then you can say fix your orientation as we discussed in the previous criterions, maybe the maximum area of the base or even the minimum area of contact with the support, which is more say your quality aspects, which it will be talking about this orientation, or minimum height of the object means your Z height is minimum criteria, and minimum facet roughness, maybe the surface finish criteria, or even the minimum volume support criteria. So like that, we can come out with say these practical example. So for how do you choose your orientation? But you may get doubt that do you have this flexibility or the option? But software by default, it may suggest some orientation. So that may be probably the minimum Z height criteria. That's more say towards the cast, minimizing the cast. That is by minimizing the Z height. That is by minimizing the number of layers. That could be the default from the software. But you may not be every time going with the default parameters or adapting it. Like it depends on your requirement and all that aspects. Then you can come out with your own say choice of the build orientation. So even you can develop some sort of algorithm or some sort of artificial intelligence kind of a stuff, where you can even say choose how automatically this part orientation for the best quality, right? So you can think in that direction also. Like you can write a code for that. Why? Because your commercial softwares may not be giving all these opportunities which it may be suggesting some orientation, and then blindly you may be going with that orientation. But if you want to do some research, some identifying some problem, research problem, and experimenting it as a user, so you can try come out with several solutions for that problems. And say your build orientation on say surface finish. Say for example, I have the layer thickness, say X is my layer thickness, and you are say going layer by layer, first layer, second layer, third layer, and so on, where Y is an exposed part area, or the gap or the error. So that error Y, the quantify it as a Y in this orientation theta. But the moment you change the orientation, so you may anticipate the Y value for this changed theta value, you have a more error here rather than this orientation. So like that, which we need to even take care about your accuracy. So which it is varying drastically from one build orientation to other build orientation. And similarly, if you're say fabricating the components in several orientations, like for example, zero orientation, which you are fabricating, and one sample, and you have another sample with the 90-degree orientation, and you try to see the fracture mechanics of these two say samples. You have a totally different fracture mechanics of these two samples, which one sample is made out of 0-degree orientation, and other one is a 90-degree orientation. So where you have to come out with your selection of your build orientation, if your criteria will be the mechanical strength is going to be. Why? Because you have totally altogether different fracture mechanics, one orientation to other orientation. And if you are looking for some say a generalized cost model for part orientation, so then the total cost involved may be the pre-processing cost, that is pre-processing in the sense while designing and while say preparing commands or the build setup. So and your design for additive manufacturing, sometimes which we need to modify the design some extent. So then you may be spending the money towards that, maybe hiring some application engineer and hiring some sort of packages to do that, or so that cost relates to the pre-processing cost. And building cost, so that is machine utilization cost. So again, depends on the polymer printing machine, or it is a metal printing machine or ceramic. So it will vary from machine to machine. So what is the machine utilization cost, and even material cost should be added. So that is both model as well as support material cost. So then that is the material cost. And post processing cost means after building, which we need to remove the supports, or which we need to clean up the surfaces sometimes, which we need to use some sort of heat treatment process and so on. So that cost involves the post-processing cost. So it's a total cost consists of the pre-processing cost, building cost, material cost, and the post-processing cost. So, right, and your good design for additive manufacturing that has been generated here in the pre-processing step as well, it will reduce the post-processing cost. Why? Because if you have taken care of your support material and your build orientation and other aspects which we have been talking about, so in designing itself, so that is a good design for additive manufacturing ecosystem, where your cost. So as we know that design for manufacturing is a cost concern, like more economical way of producing the products. So that is through additive manufacturing also, where you can cut down a lot of cost towards post processing, and as well material cost is a fixed. You can't do anything the material cost, and of course the build cost also, machine utilization and other costs involved, overheads and other stuff. But your pre-processing cost and pre-processing stage, if you are taking care of your all the constraints that you come across, and all your rules designed for additive manufacturing rules while preparing this, then you can save a lot of say amount also. So that's thing where we can focus on. Say these are the cost models that we'll be talking about. And next one is a support structure generation. So the support structure generation, say it's going to be it will vary from one technology to other technology. So even it may be a polymer based system, or a metal based system, or a ceramic based system, and some of the AM process doesn't require supports at all, but some of the AM process, but majority of the AM process requires supports. But the how do you get tackled this supports? Say you have say open source softwares for performing this operation of generating the supports, and then we need to follow some thumb rules that should be, say, if you are using some extrusion based system like FDM, and which your support overhangs less than 45 degrees, which it needs a sort of supports. So then you have as I said, like you have some open source softwares like Simplify 3D, and you have Cura or other softwares to perform this job. And otherwise also your proprietary software, which is given by the vendor along with the machine, can also be done that. And if you are having a DIY kind of a printer, so then you can make use of these open source softwares to do that support structure generation. And if you see closely the support structure design, so the support structure design, so we can divide the support structures into three categories. Say I have a platform or a substrate. On top of that substrate, we are not going to start say right from the first layer as a model component. So you will be giving a certain number of layers initially with the support material. Then normally that will be referred as a separator kind of a support, and you have a main support. So main support is one where it never directly contact with the model. So but you have the third kind of a support, so that is called a CRA or a needle kind of a support, where it has a direct contact of the model. So then we have to be careful. So while working this kind of a CRA kind of a support, the utmost care will be taken. So then otherwise it may damage your component while removing this support. So then broadly, then you can have these three kinds of supports, and each support will be having its own say significance, or which we need to focus, or which we need to handle these kind of but don't see all the supports as the same, but you have to see then which one has to be given prioritize, or what sort of support structure. We can change the support structure styles also. Then that is another flexibility we have with additive manufacturing. So then how do you tackle these support structure design or while fabricating it? So, and don't think always the support structures are no bad for fabrication, but it may sometimes will say solve certain problems. Say for example, you are not given any support here, but which we can see there is a peeling effect here. So this peeling effect can be eliminated by providing extra supports here. So where you can see these are the extra supports it has been given, where you are eliminated this peeling effect or a curling effect of these layers at the interfaces, right? So where you can, so what I'm trying to say, not always the support structures are bad. Sometimes it may be good for fabrication, but you cannot generalize this statement, but depends on the situation, geometry, and even the material, how it is behaving. So then that matters a lot. So coming to the model slicing and toolpath generation. So the once you have say fixed the orientation, and once you have say given the supports, and we need to do a next step will be the model slicing, and afterwards we need to generate the toolpath, and then slicing, the model slicing will be done. So you have the model, the CAD model and STL file, and further it has been sliced, and this is what the physical realization is going to take place. So this is the a typical slicing file that we simulate normally while fabricating the AM part. And if you see the how many number of slices that we need to get it, so of course that depends on your say the z maximum z height of the model minus minimum height of the z of the model by your layer thickness will give you the number of slices. It's simple say equation. So where you are going to get the number of say slices, and once you get the number of slices or the then how do you get the slice point coordinates, like say you have fixed the at a particular z height, means at particular a level of your model, say right from the z0, otherwise you start with first layer, and then you will be incrementing your layer thickness. So and then that is at that particular layer you are going to get the slice intersection or the slice coordinates, x coordinate, y coordinate. It's a simple mathematics involved here, the simple geometry, the which you are going to get it here. That's a simple thing. It just is a simply intersection of the plane with the a triangle edge. So we can get the x coordinate as well as y coordinate at that a particular layer. So what I'm trying to say if you take an STL file, this is my STL file. I'm talking about this is a Z0 and this is the Z max. My Z maximum is here. So if you take this is Z maximum, and I have the Z minimum which starts from here, and I have the layer thickness as say 0.1 mm. Say that is 100 microns. I'm going to slice this model, and then at a particular instance of my Z position, so my slicing plane is say intersecting my STL file, which is having the triangle. This intersect I am talking about, this coordinate of the x coordinate as well y coordinate at this Z position. So you can get these say intersection points. So that is at particular layer I'm talking about, and you keep on incrementing this slice thickness as equals to the layer thickness. So then you will be generating these slices. So then you have two possible, say, scenarios here. Either you can join these through a clockwise direction or through an anti-clockwise direction. So means either it is the inner feature or outer feature. So that will distinguish your, say, notation that you're going to adopt here. So once you get this contour, so you have the skin contour, means the outer contour you got. And even while generating, we need to even take care about the peak features. So what do you mean by a peak feature? Peak feature is one which there will be a chance of losing your feature while fabricating. Why so? So means, like, say I have say 200 micron layer thickness, say 0.2 mm, say I'm building my model. But whereas I have a certain feature here which is of say 100 micron size feature, and obviously my slice thickness is 200 micron, so I may lose my 100 micron feature, right? So then you identify if there are some peak features so that you come across in your model, and we need to give a special attention to those peak features, maybe reducing the layer thickness or changing the orientation, or you have to come out with a sort of solution for that. So you identify the peak features, and then which you should not miss them out while fabricating, right? So then that's the idea, to identify certain peak features, and then how do you say retain them in your fabrication. That's the this all will come under your design for additive manufacturing process. Why? Because otherwise erroneously if you do it, and you will be lost these features, right? So um, so then how do you organize these contours? Say for example, if you take it a particular say slice position, then you may have n number of contours at that layer position. So if you see the cross section at a particular layer position, you have n number of cross sections, and which each cross section or each contour may be the a kind of hierarchy, means a kind of a parent-child kind of a relationship. So which we need to say organize these internal contours and external contours, and the parent-child kind of a relationship between the contours. So that may be depends on your geometry of the model that you are trying to fabricate it, right? So then this is also taken care. And once you have done that, you are going to get a CLI file, or the common layer interface file. Means this is something like a G code, like which we are talking about in a CNC practice. So this CLI data will be sent to the machine. So means CLI, again, you may have a different proprietary file formats. So far, there won't be any standard file format for sending this data to the machine. So you may have CLI, SLI, and it depends on the vendor. They may have a different, say, file formats for sending it. But if you take a typical CLI file format, so what does it consist of? So it does consist of, say, contour data organizing. So total number of layers, how many number of layers that particular file is having, and the first layer, it is describing about the first layer, the layer number, this is the first layer, say, and the Z coordinate at that particular layer position, and how many number of contours are there at that particular layer. First layer, for example, how many number of contours are there, and say first contour, again, it may consist of some 5-6 contours. So the first contour, and again the contour index number, and whether it is a closed or open contour. So, and then whether it is an internal contour or external contour, which is a and then whether you have some parent for that, or the sort of linkage, means the hierarchical sequence that the particular contour is having, or it has a number of contour points. So n number of contour points, it has, say, some 10 number of contour points are there. And then what are those coordinates for X coordinate, Y coordinate, and of course the Z coordinate at that particular instant. That is for the first contour, and similarly second contour, and like that how many contours are there, all the contour information. And you have, that is about the first contour. And the second contour, again you may have a different say features, and then all that information. And like this is all about the first layer, and then you have the second layer, and again how many number of contours are there, and the contour coordinates can also be stored. And finally you have the contour data of the last layer. Like this you will be sending this data to the machine. Then once you have the outer profile or the outer contour and it is getting filled, then how do you get it filled? So then that is through a toolpath generation algorithm. Say you can fill your say cross section in several ways, maybe through combination of horizontal, vertical, or by some inclined fashion, or by contour, or by raster, or the combination of contour and raster, and so on and so forth. So then why do you need these many tool say paths? So each one will have a different effect on the layer bonding, while bonding one layer with the other layer, or within the layer, how your, if it is a powder based system, how the powder particles getting stick together. So then you have say depends on this tool path strategy, or the toolpath say filling strategy. So you can anticipate your properties at that layer and as a total say component. So which we need to even look for this optimal toolpath generation kind of a thing for as for your requirement. And mesh repair and slicer tools, where you have the mesh repair and slicer tools. So you may be using some STL editing, say for in order to do some repair or some visualization of the STL file, or labeling of the STL file, or even painting by adopting different colors. So, and then even haloing it out, or by cutting, or by Boolean operations, or by smoothing. So you can do, but you may wonder why we need to do this. So why we need to do this is, like say your native CAD system, you cannot edit an STL file. So you can generate an STL file. You have an algorithm or tessellation algorithm to save your file as STL file. But oftenly you need to do all these operations on the STL file. But it is not advisable to ask your customer, say for example you are running some service bureau, and it's not advisable to ask your customer, hey, can you measure and tell me, or can you label it, right? So then we need to have a such sort of tools to do these kind of manipulations, or these kind of mesh repairs, or sometimes we need to even do some sort of visualization, or flipping of the triangles, or flipping of the normals, or stitching of the say these triangles. So you may have several reasons why the STL file is bad, means like so you, then how do you fix those problems? So the problem here, your CAD system neither, nor your say 3D printing software which is connected with the machine doesn't have this capability. So then that's what you may be going with the other third-party software to perform these operations. And you may have the automatic triangulation, or manual repair, or you have several say options here to do a repair or modify your STL files. And support structure generation also, like which you have a sort of a block support, or a sort of a line support, or sort of a point support, or a gazette support, or web support. Means depends on the feature that it is required some support. You have a huge area, then that should be given support, then go with some block kind of a support. And you have very narrow kind of area which requires some support, you go with the sort of a line support. Or you have very small feature that should be given some support, and you go with a sort of a point support. And you have the, say you have some overhang, and which we need to go with this gazette kind of a support, or you have some sort of a circular feature, go with the web kind of a support. So like this, which you can have a different features, different supports, say, and the slicer software, which you can slice your STL, OBJ, or TMF or AMF files. Then you generate a G code. Typically, you may use a sort of software called a Cura. It's open source software, which you can generate the G codes, and further it is being sent to the machine, and which you are going to fabricate layer by layer. So you can create this slicer. So your topology, the more or less, it's more intelligent based on your geometry. It is automatically generating these supports and the percentage of fill that you are looking at. So then you can change that percentage of fill, and you can even use a different say geometries, different support structure, as we discussed previously. So you can find several open source softwares to do this job. So right from the Cura to say a Repeatide, or even you can have Slice 3R and several open source softwares to perform this job. And which I have listed here, some of the STL file repair softwares, like open source like Mesh Mixer, Netfab, or you have the other say proprietary softwares like Magix. Up to this, you have this STL say a repair say softwares, and you have the slicer softwares like Cura, Simplify 3D, and other open source softwares for say slicing the models. So these are some of the softwares, open source, as well as the proprietary softwares under STL file repairs and slicer softwares. And next part is a topology optimization. So and bionic design. So why additive manufacturing is so popular in order to fabricate these topology optimization structures or bionic designs. So I think you may come across in the recent times your parametric designing, that the previous say methodology, but now you have generative designs concept in your CAD/CAM's AE packages. You can have a generative design concept, or you can have the topology optimization, where you can have a lightweighting of the structures, and even it could be done through a lattice-based structures, or it could be done through a bionic designs or biomimicry. Say, I hope you may be familiar about the what you call the generative design concept. So that is by consolidating the parts. Means if I'm having, say for example, I have some 10 number of parts. Say my 10 number of parts or 8 number of components. Right now you have this assembly consists of 8 number of components. But whereas, so if you adopt a generative design approach, so you can make 8 components into a single component. That is through a generative design approach. And design is not the goal. I have to fabricate this. So then, which your additive manufacturing is going to play a vital role in terms of this part consolidated kind of structures where you can make use of it. So this is a generative design. Components can be fabricated, or even you can have topology optimized structures. Means I have say some sort of aerospace application like some bracket, and then I need to make it more lightweighted. Why? Because more fuel efficient system. Like, so I want to wherever possible, I want to minimize the payload, or I want to minimize the lightweighting structure concept you want to introduce. So then you can go with the topology optimized structures, where you can make use of several tools that are available to do this topology optimization. But finally, I would like to fabricate it. So you do design as for the additive manufacturing. Why? Because so this is absolutely, it may be possible through a CNC technology. I am not denying that. But where if you are more cautious or more what you call say in your mind, you are going to make it through additive manufacturing route, and then you just now we are talking about all these constraints and all these say parameters, and then can it be considered all that, and finally we can make it through additive manufacturing in a more cost effective manner, right? So that's the idea. So then you can go with the topology optimized structures, or even you can go with the bionic designs, like say so you can get inspired by the cell biology, or you can get inspired by the lattice structure, which is of more lightweighted in nature. So, and again, maybe the aerospace, medical, or you can find several applications where you are looking some sort of lightweighting structures through, say, biomimicry or bionic designs, or biological inspired designs, or lattice based structures where you can say make use of this additive manufacturing technology, right? So absolutely, say you can come out with the best usage of additive manufacturing, or design for additive manufacturing concept, where you can have these either say generative designs, or the part consolidated structures like this, or by topology optimized structures, or by bionic designs, or nature inspired designs, where you can so vary the struct size, pore diameter, and you can have a lot of freedom here, like where in terms of your fabrication. At the end of the day, I need to fabricate this structure, right? So then how do you get fabricated? So before fabricating, how do you design this? So purely you are not a mindset of subtractive here. Why? Because absolutely it is not possible with the subtractive manufacturing methodology. So so our aim is to go with a mindset of additive, and then how do you design these structures as for the design for additive manufacturing, right? So anyway, so where you can even have nowadays say functionally graded materials, like where you can extend the same logic in that aspects, right? So so like that we can keep talking about these aspects. So then you may find some of the topology optimized packages or the softwares, like say Altair OptiStruct, or you can have other softwares also, like where you can find and even which we could even do simulation kind of stuff. So why you want to simulate your builds before you fabricate it? So why do you want to do that? So why you want to do that is, say if you are not performing your simulation studies, or say blindly you are say firing the components onto the machine, so then you maybe end up with certain difficulties, sometimes build failures, or sometimes it may damage your say machine, or the recoder, or maybe it may have several problems. So then it is better to have simulate this. How do you get simulated this? You may use some say multi-physics, multi-scale modeling. So then how do you say tackle sort of say you will be working with the huge temperature gradients, right? So which you may be operating at very high temperatures, but relatively that's a fraction of seconds, or maybe you have a huge temperature gradients which you will be working at. So but you can anticipate a lot of say the sort of distortions, or a sort of residual stresses, so that has been developed within the layer or at the interfaces, where you can anticipate a lot of residual stresses, and you can even say anticipate several distortions or warpage, shrinkage problems, where you can it can be compensated once you have done a certain simulation kind of a stuff. And even you can optimize the support structures in more effective way once you have done simulation kind of studies on that. And even you can do so because of this you can minimize the risk of the printer damage or recoater damage, or even you can minimize any build tryouts. Why? Because we don't have a luxury if you talk about metal additive manufacturing, say systems. So the machine costs you around 2 crores, or the powder costs you around 20,000 rupees per kg. So you don't have a luxury to come out with say playing or destroying that parts. You don't have that luxury of so then which we need to minimize the number of build tryouts. So then which sometimes we need to predict the post processing outcomes. Maybe they say it may need to undergo some heat treatment or hipping or support removal. So where you can anticipate or we can optimize the cost rather than by adopting these sort of simulation softwares, right? So which we can done through say simulation. Through you can optimize the orientation, you can do support configuration or verifying your operating conditions, or just we discussed distortions or let's say warpage sort of errors, and then plastic strains, residual stresses, which we can say predict as well, and we can compensate. That can be compensated if it is possible, that can be done. So like that we can do that sort of simulation studies, and then you can find certain packages or the softwares. Even nowadays you can find this additive manufacturing module, so in all these CAD/CAM CA packages, so which has been meant for additive manufacturing also. You can have additive print from ANSYS, or 3D expert from 3D systems, or you can have DZMAT from Extremes, or you can have say SimuFact additive from Hexagon, and Sim Center from Siemens. You can find several commercial softwares to perform this, but majority will be focusing on the metal additive manufacturing simulations. But though you have certain polymer based systems like DZMAT or other say packages, but still you have a lot of potential. You can work on these sort of simulation studies of additively manufactured parts. You can model it, you can come out with multi-scale, multi-physics models, right? So you have a huge potential to be tapped in this direction. So for your additive design for additive manufacturing, say concepts. And say then how do you get selected your aim technology by material? Why by material means a single aim machine cannot take up all the materials. So but it may be a material specific say then in that case how do you get selected your material? So you may have polymers can be say processed, either thermoplastics or thermosets can be processed, or metals, metal alloys, ceramics, composites, functional materials or biological materials, which we can process. So you have several flexibility here, and maybe the form, maybe the well-known form, maybe powder or a filament, or maybe sheet or a laminate, or maybe liquid. So then how do you get selected your material? So but nowadays you don't have much boundaries. Why? Because when this technology was started, so if you talk about VAT based system, it used to be happened only with the polymers, but now it can be possible with the ceramics, for example, and sheet lamination also. It has started with the paper based material, but now it is possible with the metal also. So and now you talk about the powder bed system. The powder bed system also started with the polymer based system like SLS technology, but now you have several powder bed systems, powder bed fusion systems, which are capable of printing in polymers, ceramics, as well metals. So you don't have much restrictions under recent developments. So maybe material jetting so can also be possible through, though it started predominantly with the epoxy-based resins and followed by wax-based materials. But now metals can also be done through a material jetting system. And similarly for the material extrusion, though it started with the ABS or a PLA-based thermo plastics, but now it is possible to go with the metals also through material extrusion process. So you have a lot of developments are happening. And DED, so that is directed energy deposition, where you can even predominantly this is for metal printing, where you can have several options here within the metal material choices. And binder jetting also, though it started with the polymers like a plaster kind of a material from MIT, now you can even print through, and then followed by ceramics, and now metals can also be done through a binder jetting system. So, but still you cannot generalize. If I pick one technology, I cannot process, say, all the materials on that. But still, there are certain restrictions. But anyway, if you are looking at sort of a polymers, maybe a thermo kind of a polymers, maybe you can choose either SLS or FDM, or thermo sets like resins, epoxy resins, maybe material jetting, or maybe SLA or DLP based technology, or metals, maybe DMLS, SLM, binder jetting, or even DED it also can be, or you can have other material like sand, binder jetting, maybe the right choice of technology. And based on the application, then how do you get selected your EM technology based on the application? So, so before that, even in continuation with the feedstock or the raw material forms, so where predominantly maybe liquid or a powder, or this is a well-known classification of the feedstock materials. But you may have certain things as a cross linkage, powder to liquid. That is because of the recent advancements. And you may come across several principles, like maybe start from the polymerization to ink jetting to binder jetting to atomization to melting solidification to joining. Say you can have these 7 processes, so which will be having some cross connections, which it will be that will tell you the story of the recent advancements that where this technology is going in that direction. So then we'll focus on the application side, say the application. So whether your application is catered to a form fit application, so then what could be the tolerance you are expecting it, and based on that you can choose the appropriate technology. Or if you are looking for the high strength structures, maybe less than 30 MPa or 30 to 85 or more than 85 MPa you are anticipating, then you can choose an appropriate AM technology. Or you're looking some special properties, chemically resistive or a heat resistive or a biocompatible, so then you can choose an appropriate say technology. Or flexible, highly elongative, or a soft like a rubber like, then you can have the choices. So then which we need to say pick your technology or the process, so based on your application. So sometimes your application is visual appearance. You're looking for very smooth surfaces, so then you can have a certain say choices. Or you, which you have some support marks are accepted or not, then you have the other selection. Or like it is say more textures, your a wood fill kind of a thing, or metal fill, or a rubber like, or fully colored in polymers or sands. So then you can have say choices as for your requirements, the application demands. So then you can choose an appropriate AM technology. And coming to the design rules for additive manufacturing, so what are all the design rules which we need to follow? For that reason, which we need to understand the constraints of each and every process, right? So then only, so you can have a better position to, then you may get doubt why we need to work right from the scratch. Is there are any standards where directly you can adapt some ASTM or ISO standards, or some DIN standards, or some other standards, Indian standards or so, right? So yeah, but you don't have that sort of maturity in terms of standards that has been developed for the past 30, 32 years. Yeah, but still it is in a gray matter stage where we need to work in that direction. And people are like organizations like ISO, ASTM, they are working and trying to work out several standards, but still it is not up to the mark like which we can state that. We'll discuss at the end like what are the state of the standards or the certifications of these say AM printed parts. So then that is directly related to your design rules or the design aspects. Say if you take this, I took from one of the handbooks of additive manufacturing from 3D Hubs. So where you can say different values of your say constraints for different processes. Say for example, you take a feature which is of a wall support. So the wall support, the thickness of the wall support, so it may be, it should not less than 0.8 mm in case of FDM if you are at deploying, or it may not be less than 0.5 mm if you are working with a VAT based stereolithography system, or it is a 0.7 if you are working with say selective laser sintering of a powder bed nature of the additive manufacturing system. And if you're having some unsupported wall, like where it should not say less than 0.8 mm or 1 mm, or anyway SLS doesn't require any supports, then it is not the unsupported wall thing. And then you have some support overhangs. Maybe if you are working with FDM, maybe 45-degree, maybe the constraint here. And of course, SLA, it always requires supports. SLS, it doesn't require any supports. And sometimes some features like you have some embossing combination with the engraving, say then, which we need to, if you are not following this, then you may lose your feature that you are getting fabricated, though you have that in your CAD model, but it is not as it is not replicated because of these constraints, right? So then which we need to so know about these constraints, and so which we can see you have a different values for the different processes. So basically we need to understand, we need to say study these constraints of each and every process and versus your feature. And you have some horizontal bridges. So maybe it is 10 mm, not less than 10 mm with the FDM based system. So it may not be applicable for the SLA and SLS systems. And if you are looking for the minimum diameter of the hole, so the minimum diameter of the hole, so it should not less than 2 mm in case of FDM, and it is 0.5 in case of SLA, and it may be 1.5 mm in case of SLS. So you have a different capabilities of so that purely depends on, say, I understood like you may be aware that basically it is a kind of a mechanical system that you may use here, and you may have optical system here. The energy or the sort of sensors that you are going to use for your precise movements, or even for extruding it, you may use some nozzle, and you may use some sort of laser here to optically scan the surface of the wax system. And it may be the powder based system where you are going to use a recoater, and then which you are going to use a laser based system again to scan the laser particles or the powder particles. So which obviously so it will vary from one process to other process, though you have a design once you have designed this. But we need to understand so about we need to thoroughly analyze your design. So whether a particular feature is, can it be gettable or not. So we should not blame the technology, right? So better you understand the constraints of each and every process, and as for that you tweak the design, you change the design, modify the design. So if needed, if you're not able to do by using a particular process, but though you have only that facility with you, so then what we need to do? So we need to change the design, no other way, right? So otherwise you need to migrate from one technology to other technology, or like so. Yeah. So you can say discuss these 6 features with other processes, like which you can find different values for the different maybe material jetting. You have a different phenomenon, and binder jetting you have altogether different story, and the directed metal say laser systems like powder bed system. You have a different values altogether. So so once we need to say consider what kind of a technology or the facility you have, or at least your service bureau has to say communicate with you, or at least he has to tweak or he has to modify design as for the design for additive manufacturing say perspective, right? And if you are having some connecting or moving parts, say, then what could be the recommended clearance between the two moving or connecting parts? For each and every process, you have a different value. And you have some sort of escape holes. So, say then, which we need to, that doesn't require for FDM based system. Why? Because as for the demand, it is, say, depositing it. But it is needed for SLA, VAT based system or a powder bed based system, which we need to follow these sort of constraints. While whenever you have these sort of features in your design, or you are intentionally creating some escape, say, provision for your design, so which we need to say do that. And you have certain minimum size of the feature that you have to be filled, and the pin diameter or the tolerances, you have a different tolerances altogether from the different processes. So which we can find from the other values from the other processes also, which we can see altogether with the same features. You can get the different values altogether. So then what I'm trying to say, you need to understand the constraints of this, and then versus your design, say, which our aim is, we don't want to miss out these features, right? So that is our intention to do that. So then how do you do that? So then these are the things which we need to say focus on. And like from the C design labs from the Purdue University, so they have developed a mechanism, say, just you can scan through your model. So you have a design with you, and you can scan through your design. So they have categorized, or they have classified these matrices into, say, different categories. Like one will be the level of complexity, and one could be the functionality. So, and other could be the, say, you have, say, certain say unsupported features, or very thin features, or stress concentration of, areas, or tolerances, and geometrical exactness. So just you can run through your model or scan through your model, and you will get the score. So that score will dictate whether you want to say stick to the same design, or you want to have a minor modifications in the design, or have altogether is a different say manufacturing process. Means the design should be modified right from the scratch, or at least minor modifications or the major modifications. So your score will dictate whether it can be additively manufactured as a single go, or not. So then you can evaluate your design for additive manufacturing. So by this sort we can find, or you can find several other studies also, like where you can come out with some sort of your own idea, or developing a sort of some artificial intelligence stuff, say, which we can even take a decision based on that results, right? So you have a huge potential that should be tapped in this direction of design for additive manufacturing. Say, coming to the current scenario of your standards, so that is from the ISO as well as ASTM AM standards, which we can get it from these organizations. So where you have different classes of this categories of standard or standardization of these AM. Say, as on date, around 35 to 40 standards has been published, and another 40 to 50 standards has been under development. So maybe different headings like terminology, ISO ASTM terminology, that is 52900, or designers. So right from the format like STL to now is the AMF, is the newly proposed format from ASTM, and that is 52915. Or even it can be these for the purchase TM parts, you have other standards for designers. And if you're talking about the feedstock, you have a certain say standards for different materials. So Ti 64 or ELI, kind of a composition in the titanium or Inconel, or even stainless steel or aluminum, or even you have these designer um, guidelines, general design guidelines, and design guidelines for your additively manufactured parts. And for the fabrication side, again, for metal powders or polymer powders or the DED systems, you have a different standards. You cannot standardize. That is another issue. And sometimes too much of flexibility or the freedom will lead to a lot of difficulties. Maybe, as we know that additive manufacturing is meant for more into a customizing the products and more into the say complexity can be tackled with a no additional cost. But sometimes it may lead to some difficulty to standardize these, right? So, but you can have a certain leverage to do that, but still, it may be a long way to go to say, as we are enjoying a lot of standards for the conventional manufacturing process, but unfortunately, you don't have such a say liberty or sort of thing in additive manufacturing, but still it is under development. It has to wait for time to come. Okay, let me conclude here. Say what I have done for the past 1 hour 40 minutes. So we have started with the general introduction to AM and the importance of the additive manufacturing designs, and the various tools and the softwares used in additive manufacturing. And we have thoroughly discussed the process plans of additive manufacturing under the part orientation, support generation, mesh repair, slicing, tool path generation. And of course, now we have discussed certain design for additive manufacturing in topology optimization and bionic design structures, and a little bit of selection of AM technology and the design rules for the additive manufacturing. So this is what we have discussed. But the design for additive manufacturing, so the idea is to tap or rather than to exploit the additive manufacturing capability in a much say a simplified way or through the design. So can it be achieved more cost effective way, more functional improvement, you got my point, what I'm trying to say. Why? Because say additive manufacturing is a technology where not only reducing the part cost or the production cost, or also it is improving the functionality or the performance of the existing system. So that is the driving force of this additive manufacturing. So which otherwise you cannot get done through a conventional manufacturing method. So it may be a cost effective, but we cannot generalize that statement also. But the idea here is, so can it be done the more cost effective manner and more improved performance of the existing system? That's what why people are more interested towards this technology, right? So why you are talking about the industry 4.0, and additive manufacturing is going to play a vital role in this industry 4.0, right? So anyway, say let me conclude here, and before concluding my talk, say we have a facilities at NIT Warangal. We have metal additive manufacturing machine from 3D Systems, VMP Flux, and we have a couple of Stratasys make Dimension series and the Mojo series machines, and we have other desktop based printers and AnyScan, SenseScan, muffle furnace, short pinning machine for post processing of metal 3D printed parts, and AM related softwares like Mimix, Magix, Thematic, Catalyst, and 3D Expert to perform sort of simulations or medical implants design or processing of medical image data and so on and so forth. So these are some of the facilities we have at NIT Warangal. Yeah, I think I have done from my side. If you're having any questions, and then I'm very happy to answer those questions. So it's over to you, Chari. And if there are any clarifications or questions, yeah, I'm ready to take up that question.
Any questions from the audience? Any queries from the audience? You can unmute yourself and ask to the Dr. Y. Ravikumar sir.
Excuse me, sir.
Yes.
A small question only. So can we fill the holes in the tooth of decayed tooth, or we have to replace it?
Okay. So means say directly you want to fill it, means like where you can make a certain a sort of crowns or no, like no, I'm not clear about the question. Like she who asked that question, maybe better they can interact.
Yeah,
Or
it's like just as you said, a cap kind of thing can be fitted into the decayed tooth.
Yeah, you can make absolutely. People are doing that sort of practice in dental applications, like maybe your crowns, say can be, or your bridges can be done through that. So which it is very much possible. You can do that.
Okay.
You can scan it, you can reverse engineer it, and further you can make that, and through your metal systems, if you are looking permanent fixation of that thing in a jar, yeah, you can absolutely do that. Yeah.
Okay, sir. Thank you.
Sir, one question is there in the chat box, sir.
Yeah, please, Terry.
Whether acrylic plastic can be used in 3D printing to get transparent components or any other materials?
Yeah, it's very interesting question. If you see, nowadays you have almost like 100% transparent materials from the SLA based system and the DLP based systems, where nowadays is a more affordable price also. Just you can refer Formlab machines, which is our more economical machines, and you can get through this acrylic based plastics. through SLA and DLP based technologies, which is of more transparent in nature, exclusively used for dental applications or any sort of applications where you're looking sort of more transparent structures. Yeah, it's absolutely possible with the SLA and the DLP based technologies with the acrylic material, more 100% transparent, of course. Yeah.
Thank you, sir. Actually, I'm working in a fluid mechanics.
Yeah. Fine.
So I thought of a flow visualization. So if I am going to
Sure.
make a transparent object.
Yes.
So, yeah.
Yes, sir. Absolutely, it is possible. Like where,
Possible.
and it's more economical also nowadays. Earlier,
Okay.
it was very costly affair, but now it is a more economical way. Also, you can do it. Yeah, you can see through.
Okay.
These materials. Yeah, you can see through. Yeah.
Yeah. Okay. Thank you, sir.
Any questions? Any questions from the audience? Okay, thank you, sir. Thank you. Your nice session. You explained very well about the design for additive manufacturing, which type of design is required for making objects before going to the additive manufacturing. It is very nice session, sir. Thank you, thank you, sir.
Thank you, Cherry. First of all, let me congratulate you for organizing a wonderful program, which is have a blend of the industry expertise and the demo and the hands-on.
Yes, sir.
Yeah, it's very nice program, which I can anticipate and seeing the schedule. All the best, Cherry. Yeah.
Okay, thank you, sir. Thank you.
Thank you for the opportunity given. Thank you.
Yeah,
Bye-bye.
thank you.
Thank you, one and all.
Thank you. So all of you, please fill the Google form. That is, we are considering as your attendance, and please join. Whatever the time is, we are giving the schedule. On that time only, please join in the Google in the Zoom link. Okay, thank you. We will meet on tomorrow 9:30 a.m. Sharp 9:30 a.m.
Thank you,
Sir, can you send the link again?
Same
Which
link,
link?
ma, Kirtana. Today's link only.
Google form link.
Okay, yeah,
Google form link.
I'm sending now.
Okay.
I'm sending now. You can fill the form. Please, all of you, fill the Google form. This is we are consider your attendance. This is we are consider your attendance for this FDP faculty FDP program.
Sir, you are sending through chat or mail, sir?
Yeah, through chat only, sir. Through chat only. During the session or after completing the session. Okay, I'm not forwarding through mail, or I'm not sending in the WhatsApp. Thank you, sir. Yeah, we will meet tomorrow
Sir,
at 9:30
I
a.m.
did not get the link yet.
Is there in the chat box? Please check once.
No, sir, it's not showing.
No, sir, it is not there.
Not there. Oh. Just 1 minute, sir. So I'm placing here.
Maybe it is restricted, I think so.
Okay, because I will check.
Yeah, now it is received now.
Yeah, yes, sir. Okay, now you can fill the form, sir.